Question number 2. Electrolysis involves passing an electrical current through a dissolved or molten ionic compound. Sodium is a metal that can be extracted by electrolysis of molten sodium chloride. With the aid of a diagram, explain why ionic compounds do not conduct electricity as solid, however, when dissolved in water they can. Again, we've got a bit of information, but at least we know we're talking about ionic compounds and we need a diagram. So a diagram of ionic compounds show you this, which is your cations and anions. Again, we want labelled, so therefore we want to say that that's a cation and that is an anion. All right, and as a solid, the cations and anions are locked in place and cannot move. And that's a go-to response for why they cannot conduct electricity as a solid. Now, if I was to draw another diagram to show these guys as molten or dissolved, I would simply be putting these guys randomly everywhere. And no longer would they be in this lattice form. Let's say as a solution, which is what dissolved are, or molten state, for lack of a better word there, the ions are free to move and carry a charge, which allows the flow of electricity. Again, this point here is a go-to response, and the diagram basically highlights the difference between them. This is a rigid structure as a solid, whereas this is a more fluid structure as a liquid. Draw an electron transfer diagram for the formation of sodium oxide, and hence write the formula for sodium oxide. All right, electron transfer diagram again. Na with 1 electron, oxygen with 6 electrons because it's in the 6th group of our periodic table. This electron is going to go to here, but then you'll notice you have one more missing here because oxygen needs to have 8 electrons. So we need another sodium to take up the reins here and put that there. That's going to leave you with sodium positive and oxygen, or which is now oxide because it's an ion, O2 negative. That leaves us with the formula Na2O. So basically showing how sodium oxide is formed from its constituent parts. There we have it. Analysis of sodium oxide finds the sample contains this many sodium atoms. We're getting into mole territory here. Identify the number of moles of sodium. So number of moles of sodium equals N divided by Na. So therefore we're going to say we've got this many individual atoms. We're going to divide it by what a mole actually is, 6.02 times 10 to the power of 23. And I get my trusty calculator. That will give me 2.18 times 10 to the power of 25 divided by bracket. Now I'm going to try and put all this in a bracket. 6.02 times 10 to the power of 23. Finish my bracket. That gives me 36.21 moles of sodium. So now I need to go into identify the amount of sodium oxide present. So number of moles of sodium oxide. Now I need 2 sodiums for every 1 sodium oxide. So it's my number of moles of sodium divided by 2. So 36.12 divided by 2, I take my answer, divide that by 2, I get 18.1 mole of sodium oxide. Okay, and then determine the mass of sodium oxide, little m of Na2O equals number of moles times molar mass. So that's going to be equal to, what's the molar mass of this? 23 plus 16 plus another 23. So that's 40 and 63. So it's 18.1 times 63. So I'll take this number, times it by 63. Gives me 1.14 grams. And that's what, no, it isn't, sorry, 1,141 grams equals 1.14 kilograms. I messed up because I saw that little comma there. I thought it was a decimal point. learn how to use a calculator properly next time. Alrighty, so there is my answer for that, looking through a mole calculation. Remember, setting it out as to what I'm finding out, and then how do I actually translate that into my answers down below. Question 2 done.